So we're going to continue our work in chapter 6 with the normal distribution, and we're going to look at section 6.4 on the essential limit theorem. And one thing we're going to see with the essential limit theorem is that for all samples of the same size n, with n greater than 30, all right, the sampling distribution of x bar can be approximated by a normal distribution with mean mu and now standard deviation of sigma divided by square root of n. All right, so a couple key things here. Really, that sample size of n greater than or equal to 30, and our standard deviation for that sampling distribution is going to change a little bit. It's now going to be divided by the square root of the sample size. We'll talk a little bit more about that in a moment. Okay, so given, all right, whatever population we're sampling from, doesn't matter what the shape of it is, it'll have a mean mu standard deviation of sigma, and simple random samples of all size n would be selected from that population. So here are the key things with the essential limit theorem. Two things you need to know, basically, for the requirements. If you are sampling from a normal distribution, then your sampling distribution x bar will always be normal. All right, so normal maps to normal no matter what the sample size. So that's what this is saying in the first part, right? Population has a normal distribution. Now, the second piece, the or n greater than 30, is if you are sampling from a population that is not normally distributed, as long as that sample size is greater than or equal to 30, then your sampling distribution of x bar will still be approximately normally distributed. And that's where the essential limit theorem is very powerful. So even though you're sampling from something that could look absolutely not normal, the sampling distribution will be approximately normally distributed for sample sizes larger than 30. All right, now, one nice thing here, the mean of your sampling distribution x bar is the same as the population mean. Those are the same. Now, the standard deviation of your sample mean, sigma x bar, this is sometimes called the standard error of the mean. That standard deviation is now divided by square root of n. All right, so if you think of it this way, if you were sampling one member, well, square root of 1 is 1. So here's the standard error of the mean would just equal the original standard deviation, sigma. Now, as your sample size increases and gets larger and larger and larger, this standard error, right, we're dividing sigma by a larger numerical value. So this whole quantity gets smaller and smaller and smaller. So just to give you an example, if I say selected one member from the world population, say 1 out of 9 billion, okay, that person's height or weight could be anywhere on a normal distribution. They could be very tall, very small. But if I started to sample larger groups of people, say 100 and average them together, and then 1,000, and then what about if I sampled 1 million people and averaged their weights or heights together? That sample mean would really start to get close to the true population mean. Imagine if I were sampling 1 billion people on the planet and averaged 1 billion heights or weights. I think we'd all expect that that value would be awfully close to the true population mean. And so that's what the standard error of the mean is capturing. It's really the variation of your sample mean from the true population mean mu. The more members of the population that you're sampling at a time, the closer your sample mean will be to the true population mean. All right, and our z-score formula has just changed slightly. All right, now we're going to take x bar minus mu, and just instead of just dividing by sigma, we divide by sigma divided by square root of n. All right, now when you can apply the essential limit theorem is when you're sampling from a distribution that is not normally distributed, and your sample size is less than 30. So again, just keep in mind sort of that magic number. All right, as long as n is greater than or equal to 30, you can really sample from any distribution and apply our normal distribution techniques. All right, so always check your requirements. All right, that when working with the mean from a sample, verify the normal distribution can be used by confirming the original population was normal. Normal maps to normal, that's fine, or your sample size is greater than 30. All right, and again, if you have an individual value, this would be your z-score formula. All right, but if we're working with the sample mean, we make this little adjustment, x bar minus mu, sigma divided by square root of n. All right, and so this will be our notation. All right, so mean of all values, x bar, mean of the sample mean x bar is the same as the population mean mu, And this is that standard error of the mean I was telling you about, sigma x bar. That's sigma divided by square root of n. So let's look at an application of the central limit theorem. So here's the safe loading of elevators. Now this is at the San Francisco airport, and the elevator has a maximum capacity of 4,000 pounds or 27 passengers. So if 27 people are on the elevator, 4,000 divided by 27 is 148 pounds. All right, now we'll assume worst case scenario that 27 adult males get on the elevator, and the population for adult male weights has a mean of 189 pounds and standard deviation of 39 pounds. So there's our mu and sigma right there. Now there's a couple parts here, right? One, or part A, find the probability one randomly selected adult male has a weight greater than 148 pounds. Okay, so that's really looking at one individual. And then we'll look at the probability a sample of 27 adult males has a mean weight greater than 148 pounds. So let's look at part A here. So in part A, what we want is the probability that one individual male weight would be greater than 148 pounds. And remember, this is really a sample size of n equals 1. Now, the mean of our population, that is 189 pounds, and the standard deviation is 39 pounds. So remember, any normal distribution problem, right? Identify mu and sigma. Now, as I've always said, you want to draw a picture, right? So if I draw that normal distribution, now mu is 189, whoops, sigma is 39 pounds, whoops, sorry about that. And now this is our distribution, and 148 might be over here somewhere, right? So we're going to look for this probability. All right, so what we want to say here is, all right, this is really a normal CDF problem. We'll do normal CDF, and lower bound will be 148, upper bound 1E99, and of course we have to add our mu and sigma. So let's go over to the TI and do that. So I'll go to my distributions, right? Normal CDF, and there's 148, 1E99, all right? Lower limit, upper limit, 189, 39. I'll paste. And there's that probability. So rounding to 4 decimal places, we'll call that 0.8534. Okay, so let me get back over here. And I'll call that 0.8534. Right, so that's very much like the normal distribution problems that we had earlier in the course. Okay. Now, in part B, we want the probability that a sample mean, x bar, would be greater than 148. But now, n equals 27 in this case. The sample size has changed. So one thing, I'll just write it here. The mean of the sample means will equal the original mean of the distribution, all right, 189 pounds. But now, sigma x bar, the standard error of the mean, that's sigma divided by square root of n, which will now be 39 divided by the square root of 27. Now again, I always say draw a picture with your normal distribution. Whoops. And although my drawing isn't going to show it very well, right, here's mu x bar equals 189. All right, and again, 148 will be here. One thing you would see is that this distribution would have a much narrower shape, right? It's going to have much less variation, right? But now we'll still use normal CDF, and our lower bound is 148, upper bound is 1E99. The mean is 189. Now the only adjustment we have to make is the standard deviation, and like we've seen earlier in the course, with some of our functions in the TI, we can actually put in directly into the argument of the function that's 39 divided by square root of 27. All right, so you don't have to do any intermediate calculations like rounding this to a few decimal places or something like that. So let me show you how we can do that. Let's go back to the TI. And I'll use second in entry just to bring up that command again. So all I want to do is change that 39, and I'm going to make that divided by, and then I'll insert my square root function, put in 27, then just cursor out, make sure you're out from underneath the radical, and close parentheses, and I'll hit enter. And you'll see there, we'll keep that probability at 0.9999 to 4 decimal places. So here our final probability. Oops. Our final probability is 0.9999. Right, so notice the mechanics of these probs are really much the same as they are with our normal distribution probs. Really, the only thing that's changing is this part here, all right, where we divide that standard deviation by the sample size. Now, when you look at the PowerPoints, all right, this is really part A. Now, we use normal CDF directly. You don't have to convert things to z-scores, and they only do that because they're using the sort of old table method with normal probabilities. We don't need to do that. But you can see here, all right, here's our lower value, 148, upper bound 1E99, and mu is sigma. And notice sigma is 39, so you can sort of see how the distribution, it looks like a nice perfect bell curve. It's spread out. And they will come up with that same probability, 0.8531. All right, pretty much the same thing we got. There's a little bit different because of the tables. Now, what I want you to see is, when you look at the sample size of 27, all right, the original standard deviation is 39, but notice that now the standard deviation, that standard error of the mean, is 7.51. You can see how much less it is, right? It's reduced, I'd say maybe about almost by 80%, right? We're about at 40. We go down to less than 8. So it's been quite a reduction. And that's what happens, all right? As you start sampling larger and larger sample sizes, that normal distribution is going to get much narrower around the true population mean. So you can see the variation has been reduced. And so this is what the picture looks like. And you can see that narrow shape now. So this would be the distribution of sample sizes of 27. Much narrower, much tighter, much less variation around the population mean. And again, they'll use the tables, all right, they'll come up with a z-score, minus 5.46. But again, you see there's that probability of 0.999. Okay, and just to finish off the problem, then just to sort of have a practical interpretation, all right, there's a 0.8534 probability just one individual male would weigh more than 148 pounds, so that's pretty likely. But if you have a 27 randomly selected males, there's a nearly almost certain chance, right, 0.9999, that's essentially almost 1.0. It's almost certain that the safe capacity of the elevator would be overweight if 27 adult males stepped onto it. So that would certainly be an issue.